All right, welcome back, everyone. Today we're doing this integral of a floor function parameterized by this alpha is in the open interval from 0 to 1. So the first thing we're going to do is analyze the floor function. And we're going to say that n is less than or equal to x to the negative alpha. Make it a little bit simpler, which is less than n plus 1. Then, if we just flip everything, we'll get 1 over n plus 1 is less than x to the alpha, which is less than or equal to 1 over n. So if we raise everything to the power of 1 over alpha, we'll get 1 over n plus 1 to the 1 over alpha is less than x, which is less than 1 over n to the 1 over alpha. And from this, we can just deduce that x is in this following interval. N plus 1 to the minus 1 over alpha 2 n to the minus 1 over alpha. Okay, and then from here, we can obviously see that the floor function of 1 over x to the alpha is just going to be equal to n. Okay, so this implies we have the integral from the sum from n equals 1 to infinity, because if you see here, we can add 1, that's fine, but we can't divide by 0, so n is not equal to 0. Let's go ahead and write that down. Okay, so the integral, sorry about my allergies, by the way. They're pretty bad right now. Pull that in out, we'll just get dx. And that's not a 0 or 1 either. Sorry. N plus 1 to the minus 1 over alpha to the n to the minus 1 over alpha n. We'll put a little dx right here. Okay. So now, I'll just scroll down a little bit and swap colors. So we have I is equal to the sum from n equals 1 to infinity of n times n 1 over 1 over n to the 1 over alpha minus 1 over n plus 1 to the 1 over alpha. I'm going to start writing out some terms for this, because I have a feeling there will be some actual cancellation, and we can just simplify this entire sum, and it'll make everything a lot easier. So if we plug in 1, we get 1 times 1 over 1 to the 1 over alpha, so we'll minus 1 over 2 times 1. So we'll get 1 minus a half to the 1 over alpha plus, plug in 2, we'll get 2 times a half to the 1 over alpha minus 2 times a third to the 1 over alpha plus, and we plug in 3, we'll get 3 times a third to the 1 over alpha minus 3 times a fourth. I can't really fit it in there, but you kind of get what's going on. You can see that you can combine these, sorry, not those terms, these terms, and you get 1/2. Sorry, I'll just rewrite it. You'll get I is equal to 1 minus 1/2 to the 1 over alpha. And sorry, that's plus 1/2, plus 1/3 to the 1 over alpha, plus 1/4 to the 1 over alpha, plus 1 over k to the 1 over alpha. Okay? So that'll actually just be n, right? Yeah, whatever. Basically, we get I is equal to the sum from n equals 1 to infinity of n to the minus 1 over alpha. And now I'm going to go over here and just write down, nope, zeta of s, Riemann zeta function, is the sum from n equals 1 to infinity of 1 over n to the s. Sorry, that's a terrible s. I'm going to write at an angle here. Okay. Now, if we set s equal to 1 over alpha, we get, this implies that we get zeta of 1 over alpha is equal to the sum from n equals 1 to infinity of 1 over n to the 1 over alpha, which is exactly what we have over here. So this implies that the integral I is equal to the integral from 0 to 1 of the floor of 1 over x to the alpha dx is equal to zeta of 1 over alpha, which is pretty cool, but this is not true for all alpha. Just because if we take alpha equal to 0, which I'm now going to make this a function, I of alpha, I want to figure out what the whole domain of this function is. So for the values between 0 and 1, we have basically going to have an f of x here. We're going to have our zeta function, and then another f of x. And this is going to be x less than 0 or equal to 0. This is going to be x. This is going to be 0 is less than x is less than 1. And this is going to be x greater than 0. So, and sorry, that's just false. These are not supposed to be x's. These are supposed to be alphas. Okay. And so obviously we can't plug in 0 for alpha. So we need some new function up here. So let's start there. So for I of 0, we're going to have the integral from 0 to 1 of the floor function of 1 over x to the 0, which is obviously just 1. So we'll have the floor function of 1, which is just 1, so we'll have dx, which is 1. What about I of -1? Or wait, what about I of a half? No, that's a -1/2. I of -1/2, we would have integral 0 to 1 of floor function of 1 over, which would be, that would become 1 over the square root of x. That would just be the floor function of the square root of x. Obviously, this is already a lot harder. But let's think about this. The floor function is going to be 0 for all, because think about this. Let's call this function f of x. That function is f of x. The square root of x between 0 and 1. So like we have the square root of 0 equals 0 and the square root of 1 equals 1, right? So if we're using the floor function here, we're always just going to get 0 because a single point, 1, doesn't have any measure, basically, which means that this is equal to 0. So for any, so we'll have, okay, so we'll have, we have this definition for our I function. This I of 0 has a special value. Any number less than 0. So we have something, we need to get rid of this. Any number less than 0 will be zero, basically. So we have, let's see what we have so far. Zero is, I of alpha is equal to 0 if alpha is less than 0. It's equal to 1 if alpha is equal to 0. And it's equal to, sorry, this zeta function, zeta of 1 over alpha, if alpha is in between 0 and 1. And now what about this last function? So what about alpha greater than 1? So let's just do this over here in a different color. Maybe this color. So for alpha greater than 1, we have I. Well, let's do I of 1, because we know zeta of 1 is undefined. So we can't use the zeta function to evaluate that. So obviously for 1, we'll get the floor function of 1 over x, which is undefined, I believe. Because as this function goes to 0, you blow up to infinity. And I'm 99% sure. Yeah, that's divergent. So that is undefined. I think I of 2 would also be undefined. I think this function cannot be bigger than 1 at all. So let me know if I'm wrong about that, but I think this is our full function. So I'm just going to say assume that that's true, because I don't really want to work through it right now. It's kind of late at night and I kind of feel sick, but I thought this was a really cool problem that I found. I was just messing around with like, step functions, and I was able to find this cool piecewise function involving the zeta function, which was really cool. Holy crap, I cannot draw a zeta. Sorry. There we go. 1 over alpha. Sorry, I did not mean to zoom out. Alpha is less than 0. Alpha is equal to 0, and 0 is less than alpha is less than 1. That right there will be our full definition for this final function. But obviously the coolest definition for this function, or for this parameterization of this function, is the closed interval I put at the beginning. I was just kind of messing around there trying to figure out, what was going on with the function itself. But we do know the cool fact that this is equal to zeta of 1 over alpha if alpha is in the open interval 0 to 1. Very cool. Thank you for watching, and that's all.